I'm Eleanor Miko, and I will be sharing an overview of my research project on atmospheric photochemistry at the Organic-Aqueous interface. My mentor for this work is Professor Sergei Neskorodov. Clean air is one of the precious resources that is essential for all of us. Despite its importance for our well-being, air pollution continues to be a significant problem globally. Those of you who grew up in the Los Angeles area are likely familiar with the many air pollution challenges faced by this region for decades. This picture shows an example of a dense smog cover engulfing the city skyline. When the sunlight interacts with air pollutants, reactions take place leading to the formation of the smog. While research on this topic initially focused on the air through gas phase chemistry, my research group views the subject from a different perspective: the pollutant particles themselves, called particulate matter or aerosols, where dynamic processes can take place between multiple or even within individual particles. This is what my project seeks to model: reactions occurring between different parts of single aerosols. On the left is a picture of a real aerosol, which has water in the center, called the aqueous phase, and an outer coating of organic goo, so to speak, referred to as the organic phase. This scale bar represents 20 microns, or about a 500th of a centimeter. Because these aerosols are so small, I needed to scale up my model. To do this, I aimed to capture the complex nature of these interactions in a beaker, as shown here. Like oil and water, these phases do not mix, limiting the possibilities for components in either to ever interact with one another. However, there is one exception. At the boundary between phases, the interface, these components are able to meet and react. The objective of my research project was to utilize this model of phase-separated aerosols and investigate what products form from the reactions in this unique environment. Exposing the system to an artificial light source modeled how the sun's radiation could spark reactions leading to product formation. By using both classical techniques and sophisticated analytical methods, such as spectroscopy and mass spectrometry, I was able to detect when products formed and assign their identities. So far, signs of reaction have been observed. However, it has also been difficult to confirm whether they have occurred at the interface, and some changes have been small. This work has shown me how challenging these systems can be to accurately model and research. This has been one of the reasons for the currently limited scientific understanding of multi-phase aerosols. Projects such as mine have the potential to increase our knowledge of this area with possible impacts to air pollution, such as the examples nearby in Los Angeles, and therefore our health, as well as Earth's climate. For this reason, I'm continuing work on this project, and fortunately, we still have some tricks up our sleeves. By testing different light-absorbing molecules that can capture and transfer energy to other model components, I can further refine the interfacial environment, which I hope will lead me closer to my objectives and contribution to this important area of research. Before I conclude, I would like to thank Professor Sergei Neskorodov for his mentorship and all of our group members for their support, as well as UCI Europe for providing funding for my research. Thank you.